So I'd like to go through another example of doing impedance computations. And in this one, the problem is going to look slightly different than the other one, at least in the initial setup, but it's going to still be essentially the same thing that we're going to do here. Now this one actually might be easier than the previous one we did. We're going to find the equivalent impedance still, Z equivalent. Now one thing you might notice right away that's different is notice that I haven't specified a frequency for you. And there's a reason I haven't specified a frequency. Look at the problem. The inductor and capacitor already have the impedances computed for us. So sometimes the problem will give us these inductors and capacitors with their impedances already computed, just so that we don't have to do extra work to compute these impedances. And sometimes on a quiz I'll do that, because sometimes I'll have questions on the quiz where I'm wanting to, see if you can use the formulas to compute impedances, and then I want to have a question to see, well, do you know how to find equivalent impedance? Not so much, do you know how to find the impedance of the components? Because if you were to find the impedance of the inductor wrong, of course your equivalent impedance is going to be wrong. So sometimes I'll give it to you like this, so I can see, can you combine things in series and parallel correctly? All right, so we said the typical rule of thumb is, again, we start at the opposite end of the circuit. And if I start at the opposite end of the circuit, I start over here at this 20. And I say, okay, well, this 20 looks like it's in series, but wait a minute. This 20 here, it's in series, but if I look here, this actually, I have to be careful with this. That right there is something that I have to take care of first. And those two components here, that inductor and capacitor, are in parallel. So I'm going to go ahead and actually just use the multiplying formula, J4 times minus J10 over J4 plus, or I should say, yeah, plus minus J10. And so let's do this multiplication out. Now we have minus J squared 40 over, now I'm adding, so this would be minus J6. Now, yes, we do know that J squared is -1, but you don't want to rush and always do that, because what I can see here is I have a minus J here, and I could cancel that, and I'd just be left with a J up there. So really, this is just simply J 40 over 6, which would be J 20 over 3, which, what is that, like J 6.67 ohms. Now you can always double check your computations, make sure I did everything correctly. But, and again, you can use your calculator to do this. I worked it out by hand here, but you can use your calculator. So now let's draw the circuit that I have here. Now, when it's in this state here, the most common mistake I see people making here, once we get to this point here, is they want to put a circle around this whole thing and say, oh, that's all in series. That is 100% wrong. All three of those components are not in series. Because again, look at this wire here that I've got sticking out at the end here. There are 1, 2, 3 things connected to this node as well as to this node. So this resistor is not in series with these other components, this 10 ohm resistor. But we absolutely do have that these two components are in series. So doing those in series, well, it's kind of a little silly, but you'd have 20 plus J 6.67, which is equal to, nothing combines together. So that's 20 plus J 6.67 ohms. And so now my circuit, if I redraw it, looks like the following. This is a 10 ohm still, and then this is J, I'm sorry, I can write the J first, but I should always write the real first. 20 plus J 6.67. And now I clearly have, if I look at these two components here, those are clearly in parallel. And so doing the parallel combination, again, the kind of multiplying method, I'd have 10 times 20 plus J 6.67 divided by 10 plus 20 plus J 6.67, which is equal to 200 plus J 66.7 over 30 plus J 6.67. Now we just need to do this computation out here. And if we do that computation, let me go to the online calculator again here. What do we get here? Well, let me go back here. We have 200 plus J 66.7. So 200 plus 66.7 I divided by 30 plus 6.67 I. Hit enter, and we get 6.82. So this is 6.82 plus J 0.706 ohms. Now again, if I were to ask the same question here, what two components could we use to represent this? Well, the first component should always be easy because the real part is always a resistor at the value there, so 6.82 ohm. And now the only question is this term here an inductor or capacitor? Well, again, we turn to looking at the sign because it's positive. Because that's a positive there, that means it would have to be an inductor. And it would be an inductor of impedance value J 0.706 ohms. So those two components could represent the equivalent impedance. Now I said they represent the equivalent impedance. They absolutely do not represent the circuit. And I want to emphasize that because don't think that you can, like if you build a circuit like this, because this circuit will, this actually has an oscillator in it here. This is an like LC capacitor and inductor in parallel like that can give you an oscillator here. So we can have some kind of oscillations going on in this circuit if we put a voltage on it. Don't think that you're going to get an oscillating circuit if you attach a voltage to this circuit right here. You will not get the same thing at all as far as like what the characteristics of the outputs would look like. This is just talking about equivalent impedance. And the purpose for equivalent impedance it's not the sole purpose, I should be careful, but one of the most important things for equivalent impedance is going to be max power transfer. Because if you remember with resistors, you would set the load equal to the Thevenin resistance, or what we called the equivalent resistance. Well, we're going to do something similar to get max power transfer when we have circuits with both capacitors and inductors present in them. All right, but we'll end the video here. And believe it or not, we're getting pretty close to being done with this section here in this chapter. The only thing I'd like to do is do one or two examples of analysis techniques with sinusoidal steady state to give you some help with that. And then that will be it for these videos.